Here's a picture of image formation for an object that's close to a diverging lens. Okay, remember the previous object was further. We see that this ray that goes through the center is steeper. This ray still goes out at the same angle, but when they converge, since this ray is steeper, that makes the object a lot bigger. So as we saw, as we move the converging lens closer, or the diverging lens closer to the object, it gets larger, and when we move further away, it gets smaller. Okay, let's see. It looks like either I've got the wrong lens or the lens has a leak in it. Get a little water here. Okay, I think I've got a leaky lens. But there, and as we move away, the object gets smaller and smaller and smaller. Okay, larger, smaller. And you've just seen the explanation for that. The focal length of a spherical lens, as we've seen, depends on the index of refraction and the radius of the lens. And we can trace the rays. We could work it out mathematically. If we have a thin section of a spherical lens like this, cut out of a sphere, or broken out of a sphere, as lenses that we use here have been, we can determine where the focal distance should be. Okay, depending on the thickness of the lens and the radius of curvature and the index of refraction, we get a certain focal length. Now, for the lenses that we have here, Josh made some observations. Okay, for a 3-inch water lens, that is a water lens broken out of a 3-inch sphere. This is a 4-inch sphere here. 3-inch sphere is naturally somewhat smaller. We have lenses broken out of both types of spheres. But the 3-inch water lens gave us a focal distance of about 12 centimeters, the 4-inch lens about 15 centimeters. Now we viewed an object, actually a person. We illuminated a person at one end of the room, 3.5 meters from the lens, and we observed the image of the person. Okay? Assuming a focal length of 12 centimeters, and Josh got the focal lengths by shining the laser, keeping it parallel, the whole procedure of your experiment. You got approximately this focal length. Now you might be able to get a more accurate focal length. This isn't bad. It could be improved upon a little bit, but it's not a bad result, and probably close to the result that you got if you did the experiment correctly. Okay, the focal distance is 12 centimeters. Using the 1 over f, 1 over the focal distance of 12 centimeters equals 1 over o, the object distance of 3.5 meters or 350 centimeters, plus 1 over I tells us that the image should have formed at about 12.5 centimeters. And indeed, that's where the image, the sharpest image, did seem to form, at about 12.5 centimeters behind the lens. The image size should be image distance over object distance times the object size. Again, just by similar triangles that we could draw here. A triangle here for the object, a triangle here for the image. They're similar triangles, and the bases of the triangle are 3.5 meters and 12.5 centimeters, so that the ratio of the triangles will be 12.5 to 350, and that's what our image size is going to be. It turns out about 2 inches, and that's about what we observed when we measured the image. So the image did appear to be about 2 inches high. Fairly sharp image. Again, you can do this with your television set or with any brightly illuminated object. Last thing we'll talk about on this lecture is what happens if you have two lenses. Okay? Well, let's see. If you got two lenses, let's say you got an object here and a converging lens that forms an image of that object at some point. Okay? And then you put another lens out here. Well, this is a real image. It doesn't really matter if it's virtual or real, but we have this image, and this image becomes the object for the next lens. The next lens thinks that there really is an image there, if you want to anthropomorphize things. Okay, so you have an object, a real image or a virtual image, it doesn't matter. This image becomes the object for this lens. Okay, so the image of the first lens is the object for the second. And then the second lens forms the final image. Okay? And we can tell by tracing the principal rays. Usually the ray coming in parallel to the axis and the one through the center is sufficient. Sometimes the ray that goes through the focus on this side is used also. By tracing the rays, we can see where the images ought to be. Two lens systems are used in microscopes and telescopes. And the type of image you get and the location and the nature of the image, the magnification and so forth, simply depend on where you put the lenses with respect to the images. If you want a big magnified image, what would you do? You would take this lens and move it until the image of the first lens is close to the focus. Okay, because that's where you get the maximum magnification. Of course, you see from the water lenses that those images are often pretty well distorted. That's because the water lenses are spherical, or sections of spheres, and they distort the image. Okay? But for a well-made lens, you might get a very sharp image, and of course that's what you're after.